let me just put the first question. So yeah, you have a linked list as an input, head of a linked list as an input. A node is a critical point if it is a local minima or local maxima. And as name suggests, local minima maxima are nodes which have values strictly greater or strictly less than its previous and a next node. So given such a linked list, you have to return two things: minimum distance between any two critical points and the maximum distance between any two critical points. So yeah, so go through the question and the examples and let me know like if you have any doubts.
Okay, so a node is a local maximum if the current node has a value strictly greater than the previous node and the next node. Okay, that makes sense. So it's like the maximum, it's like the peak node. So between those two nodes. And then a node is a local minima if the current node has a value strictly smaller than the previous node and the next node. So that's like a valley. Note that a node can only be a local maxima, minima if there exists both a previous node and a next node, right? So if we're at the head or we're at the tail of a linked list, we cannot be a local maxima or a local minima. So given a linked list head, return an array of length 2 containing both the minimum distance and the maximum distance, where the min distance is the minimum distance between any two distinct critical points, and max distance is the maximum distance between any two distinct critical points. If there are fewer than two critical points, return -1, -1. So a critical point is a critical point either a local maxima or a local minima? Okay.
Yeah, it could be between any two critical points. It doesn't need to be between two minima or two maxima.
Gotcha. So it could be a local minima and a local maxima, or vice versa.
Between two minima or between two maxima. Yeah.
Gotcha. Okay. Okay. So we want the min distance and we want the maximum distance. So, okay, so now looking at the examples down here, the first example makes sense. The second example, so we have 5312512. So if we look at the one there, the first one that we see, that's a local minima. And then we have a local maxima at 5 because 2 and 1 are smaller than 5. And then we have a local minima at 1 at that last one there because 5 and 2 are greater than the 1.
Right.
And so those are the three critical points. And so the minimum distance is between the 5th and the 6th node. Okay, so basically as we're going through the linked list, we need to check, we first determine, okay, is this node local or a local maxima or a local minima? And then we need to basically just find the minimum distance and the maximum distance. Okay, so just thinking out loud here, if we loop through the linked list and we recorded the positions, the indexes of the critical points, how can we get the minimum and how can we get the maximum? So we're looping through 5, 3, 1. That's our first one. So we could keep track of the leftmost critical point. So right now I'm just thinking out loud about like a 2-pointer approach where we iterate through the first one that we see, we move our left pointer to that value. So we set that to the index of 2 and the value 1 for our left pointer. We keep iterating through, and the next one that we find is 5. And at that point in time, that's the next critical point. And since we found the next critical point there, we know that there's a distance of 2. And so we can, when we find a distance, we can just store, we can keep track of the min and the max. So at this point, the minimum is 2 and the maximum is 2. And then we move to 1, and once we move to 1, our maximum would become 3, and then what we want to do is update the left pointer to move to the 5, and then store that as the minimum. Okay. And then the other thing so that makes sense. Right now I'm just wondering if there's like a binary search approach, because these are peaks and valleys, and when you have peaks and valleys, I feel like a binary search approach can work.
But will the binary search work on linked list?
No, I think you'd have to convert it to an array.
Right,
and then
but
you have
then
to.
if you are converting it, you are anyway taking linear time.
Right. So yeah, that makes sense. So worst case or best case scenario in that case would be O of n. So okay, that makes sense. So yeah, binary search approach wouldn't be valid for this solution. So I'm going to start coding here. So let's thinking about some constraints here. So for input, it looks like we get the head of the linked list, and then for the output, it looks like we're just looking for an array or a 2-element array. Is that true?
Yeah.
Okay, cool. And that would just be the values of the 2 values. So, or the 2, I'm just checking to see. So the min distance and the max distance. Okay. And then what is the maximum amount of items that we can see in the linked list?
You can assume 10 to the power 5.
How many? Sorry.
10 to the power 5.
10 to the power 5. And then minimum?
It could be null.
Could be null. Okay. All right, I'm going to start coding here. So we have the head, and we want to I can't type. Okay. Well, okay, so we'll loop to the linked list, and we want to keep track of the index in the linked list. And we also want to kind of have like a left pointer that we can update. So we'll start with that. And so while we're looping through the linked list, starting at the first node. So the first node we know can never be a critical point.
Right.
But so we probably want to keep track of the previous node at each step. So we'll start with previous equals none. And then we'll set the previous to the current node. And so this way, so the first step that we get in here, previous is none. But if we have a previous value, we can check to see. So if we have a previous value and we have a next value, we can check to see if it's a critical point.
Mm-hmm.
So if we have a previous node and the next value, then we want to check. So if previous.val is greater than, and I'm just checking here, so it would have to be greater. Okay, yep. So if the previous value is greater than the current value,
Mm-hmm.
and the current value is, or and the current.next value is greater than the current value,
Mm-hmm.
then then we have a local minima.
Mm-hmm.
The other thing that, and then so we'll also check for, let's do this, is critical. Debating on how I want to organize this. I guess we'll just do one big if statement for now. Okay, so if the previous val is smaller than current value and current.next val is smaller than the current val, then in that case, we want to so if our left is not set,
Mm-hmm.
we want to update it to that critical point. And then when we find the next critical point, then we want to capture our min and our max. So I'm going to
Mm-hmm.
initially set left equal to -1. I'm going to add a couple more variables here. So minimum critical point is equal to let's set it to this for now. Okay, so in this case, we found a critical point. Let's set left to none actually. So if left isn't set, then we just want to set it here. So we want to store the index I, so left equals I. Otherwise, if left is set, I think at that point in time, we can, so it is a critical point. At that point, we can measure the minimum critical point and the max critical point. So and that's going to be I minus left plus 1, and the max critical point okay. So looking at our example here, but we get to 5, 3, and then 1. 1 is a local minima. And so we store that as a critical point, or so we store that as our left index, and then we keep moving on. We get to the 5. Since we have that left index in there, we subtract the difference, which is 0, 1, 2, 3, 4. 4 minus 2. And so is the distance 2 or 3?
So it could be the max distance could be between like any two critical points. So you're working on the second example or which?
Yeah, I was just looking at the second example there.
Yeah, and the distance would be 2, right?
I think so. Okay, so I don't need the +1 there then. Okay, so and then so if we find it, so we want to keep. Here's what I'm trying to figure out is that we want to keep a reference to the farthest index. Okay, so if we're being greedy,
Mm-hmm.
we can keep a reference to we know that we always need the leftmost critical point to find our
Mm-hmm.
maximum. But to find our minimum, we always want to update that critical point. So we actually need 2 pointers here, not just a left pointer, but our left max and our
Mm-hmm.
left min. And we can do this using like a greedy approach, where basically the first critical point that we see becomes the one that we use for our maximum, and we never reset it. So, and then the min we always update. So left, but we do it after we. So, okay, so for the max critical point, that makes sense. And then we want to set the left min
Mm-hmm.
is equal to I. We always want to set it, but we want to calculate. This will always equal 0. So we need to make sure we set the left min after we calculate the minimum critical point.
Mm-hmm.
But if we don't have an initial one,
Right.
we do need to set it.
That's correct.
So left min equals I. Okay.
So left mean is leftmost point or rightmost point, or the last
Yeah,
critical
sorry,
point.
the variable name is not great there. So this would be the left min is actually the rightmost point. So this is,
Let's say the right, yeah,
so
most
we'll just call this
on the
the
left.
right critical point. I
Mm,
guess we'll call it rightmost critical point, just to be
sure.
very specific.
Right.
And this is leftmost critical point.
The first critical point. Okay.
There we go. And this is, okay, so using our example, or let me just make sure I'm not missing anything else here. Then we want to return the min and the max. And
Mm-hmm.
then, and if it's, we'll do a little check here. So, out, infinite, there,
Mm-hmm.
there, that'll convert it from infinity. So in the case where we can't find one, we'll turn it from infinity or negative infinity into -1. And so, okay, so now I'll go through the example here. So I'll use the second example. So we go 5, 3, we get to 1, we find our local minimum. So we set
Mm-hmm.
our, since the leftmost crit point is not set, we set that and to I. And then the rightmost script point is also not set, so we set that to I. And then we find our min and our max. At this point, the min and the max are 0 and 0. So we would update those. And we
I
set
think
our
yeah,
rightmost script
this
point.
this will work for these examples. What if like linked list has just one element or linked list is null?
Yep. So those are some edge cases that we need to take care of. So if
Mm-hmm.
the linked list is null, we just want to return -1, -1.
Mm-hmm.
And then what was the other one that you said? The other scenario?
It just has one element.
It just has one element. So if it just has one element, then we know that we can't get one either. So if head.next is none, then we can return this and we can combine this into one statement.
Yeah. So let's say that even in the normal case, like with the second example, when will your while condition terminate?
So the while condition will terminate when we get to the end of the list. So we could terminate right before the end of the list. So we never need to actually look at the tail node. So we could actually say, well, current.next here instead of current,
Mm-hmm.
because if there is nothing, yeah, so is that correct? I think that's
Yeah.
correct.
Cool. Now it will work. Otherwise, it will give like current.next would have given you null pointer thing.
Say that one more time, sorry.
Now it makes sense. Otherwise, current.next would have given you the null pointer exception because like
Right. So so if next is none,
yeah.
so we are checking this here. So it
Oh,
wouldn't
wait.
be, we wouldn't see an exception,
Okay.
but we can actually remove that check now. So we can just do this since we're doing that in the while clause.
Okay. Cool. I think yeah, this is good. Let's move to the second question.
Okay.
I'm pasting at the top. So you have an array as an input, and basically you have to return a true if it is a mountain array or not. A mountain array is an array which has at least three elements, and there exists an index I, such that the array is strictly increasing till that index, and array is strictly decreasing after that index. And both of these increasing and decreasing parts should be non-empty. So yeah, again go through the question and let me know if you have any
Okay.
doubt.
So given an array of integers array, return true if and only if it is a valid mountain array. An array is a mountain array if and only if array.length is greater than or equal to 3. So we need at least 3 elements. And there exists some I with 0 is smaller than I, is smaller than array.length minus 1, such that, okay. So example 1, it needs 3 elements, so that's false. Example 2, we have 3 elements, but we have no peak because 5 is equal to 5, and the last 5 would need to be 4 or less to make it a valid mountain. And
Right.
then example 3, we have 0, 3, 2, 1. 3 is a valid peak because 0 is less than 3 and 2 is less than 3. Therefore, it's a valid peak. So,
Uh,
um,
yeah, it's not about just one peak. It should keep on decreasing also. So this is not, for example, if this would have been like this, it would not be a mountain array.
oh, okay. So,
So basically, once it start dipping, it should keep on dipping till the end of the array.
I see. Okay, so there can only be one peak basically in the array. If there's more than one peak, it's not a valid mountain array. Okay, so the easiest way to do this uh, would be an O of n operation where we loop through the array and we validate that it's increasing and then decreasing in some way. So looking at example 3, um, we make sure that it's increasing initially, and then when it starts decreasing, it never stops decreasing. That part seems pretty straightforward. I wonder if there's a binary search solution here that we can do in log n time instead of O of n time. So if we binary searched for, if we did a binary search, what are we looking for? We're looking for the highest, we're looking for the maximum in the array. So the highest value. But even if we find the highest value, we have to confirm that every element is still either increasing if it's to the left, or I guess if we're starting at the highest element,
Right. Even like
we have,
even for finding the highest, right? You're not sure, like because you are not guaranteed that this is a mountain array, right?
right, right.
So
Yeah,
yeah. So
and
even
to
finding
even
the peak
find the highest, sorry.
is not always guaranteed. Yeah.
Yeah, yeah. So this binary search wouldn't work for this. So, okay, so I think an O of n operation here where
Mm-hmm.
we iterate through, we verify that it's increasing and then decreasing would work. So I'm going to type up that solution.
Mm-hmm.
Okay, so the inputs in this case are going to be an array, and the outputs are going to be a Boolean. And the inputs, those are, so are the inputs always integers? Is it an integer array? Or are you there right now? I can't hear you.
Hey, hi. Yeah, I lost you for a bit. What was you
Oh,
saying? Like,
is it an integer array for the input?
yeah, you can consider it as an integer array, but it could be negative also.
Okay. And then what are the maximum values of the integers in the array?
I can assume 10 to the power 6 and 10 to the power minus 6. Minus 10 to the power 6.
Oh, did you say they can go negative too?
Yeah, yeah.
Okay. Um, if all of the integers are negative,
Mm-hmm.
uh, can we still find a mountain?
Yeah.
Okay, just making sure. And then what is the maximum and minimum length of the array for the constraints? I think I lost you again.
Y
Oh, never mind.
yeah, so maximum, so basically, your array length could be 10 to the power 7, and your increasing part could be 10 to the power 7, like just one, in a valid case, your increasing part could be of length 2 only, and your decreasing part could be of length 2 only, at, in the extreme case. Yeah. So it should be non-zero increasing or non-zero decreasing. It doesn't need to be like in between. That peak of a mountain array doesn't need to be at the in between of the array.
Okay, sounds good. Um, So we start looking through the array, and
Mm-hmm.
so I'm just going to handle some of the edge cases first. So if the length of the array is smaller than 3, we can just return false right away. So this guarantees that we can start from the first node and end before the last node or last element. So we can check before and after. So if so in this case, if the left node or element is smaller than the current element, and the current element is greater than the next element, then we've found our mountain. But then after that, we just need to make sure that everything is decreasing after that. Because before, okay, cool. So we found our mountain, just make sure everything is decreasing. So we could say, what we could do is just use a mountain index equals set the mountain index and then break and then do one more for loop to finish it out. So we would start from the mountain index plus 1. So if we never find a mountain, we need to quit out as well. So if mountain index is equal to -1, we need to return false. And then now we just need to make sure that the array is decreasing. And so we can use the previous value because that should be the greatest value initially. Why is this not happy? I'm not sure why this is not completely happy, but
Because you have not declared I, right?
oh, right. Sorry, I messed that up here. There we go. So the previous value is equal to the array at mountain index, and then there we go. And then so before we reset the previous value, we can use that for our current iteration and make sure that the array at I index is smaller than the previous. And if it's not, we want to return false. And we can return true at the very end because that will indicate that the array is decreasing. So I'm just trying to think if there's any other edge cases that I missed here. So we make sure that the array is of length 3. The first mountain index that we find, we just make sure that it's decreasing after that. If we can't find a mountain index at all, then we return false.
That's also correct.
Cool. Yeah, I can't think of any other edge cases at this point. Yeah.
Um, can you look at this condition once? Line number 25.
Yep.
Oh, okay,
So,
sorry. You already have length minus 1. Okay, so it won't go out of bound.
yep,
Yeah, so that
yep.
is taken care of. Mountain array, it's mountain index is minus 1.
Oh, actually, there is one thing I missed here.
Then,
This on line 33 there, I want to go all the way to the end of the
mm-hmm,
array to make sure it's not increasing at the
mm-hmm,
very end.
right, okay. Yeah, okay, you're looking at the previous one, so you have to go till end. Okay. Mm, accepted, that's just fundamental false, otherwise, otherwise it control. I think, yeah, this makes sense. It will work. Yeah, so you don't need to run through every test case, but can you think about different kind of test cases which will make sense for this code?
Yeah. So, I would want to do some happy path edge cases. So cases where
Okay.
the array has one mountain. I'd want to add test cases where
Hmm.
there's multiple peaks and verify that it returns false. Um, I'd want to
Okay.
verify that if the length is smaller than 3, that it always returns false. If, for example, we
Hmm.
had no peaks, right? So if we just had like example 2 there where it's
Increasing or
355. Yeah,
hmm.
it's like only increasing or only decreasing, um, that it
Hmm.
always returns false.
Hmm. Cool. I think,
Yeah.
yeah, I think this is good. Yeah, I don't have any other questions, so let's pause for feedback. Uh, I think, yeah, you did really well in terms of like all of the things. Like I really like the way you clarified the question. And I really like the way like you shared your approach before going into the implementation details. And the speed of implementation is no doubt is really good. So yeah, I think like based on this interview, I would have definitely given a strong hire call.
Awesome.
Only thing which I would recommend, which if you have such a good, I would recommend this to only candidates who have good implementation skill, is that once you write a code, think about opportunity to modularize it a bit. For example, in the first code, I think like its critical point is something which you can extract out from line number 88. You could make it that condition as one function.
Yeah.
Yeah,
Yeah.
only that is only small thing I'm saying. But do it at the end. Don't think about writing modular code right from front because at Meta the
Mhm.
speed is important. Yeah, so that is the only thing in terms of improvement I would suggest.
Okay.
And yeah, and I think like other things you might be aware about Meta interview is that coding interview does not indicate like level. So if you are giving a coding interview at Meta, so interviewer just has one thing to talk about whether this candidate has good enough skills, coding skills for Meta or not. It does not have
Mhm.
any indication about which level the candidate should be hired upon.
Mhm.
Only system design and behavioral interview decides the leveling part. So yeah, so that is the thing which you can keep in mind. Um, yeah, I think like along with like coding, like do focus on system design and behavioral part. I think like one thing which in behavioral part is important to keep in mind is Meta has very impact-driven culture. So whenever you're talking about any projects or your previous example, if you can conclude those examples with numbers, let's say for example, how much cost it saved you for your company because of this,
Sure.
or how many, or in terms of requests also, like previously it was catering only 2,000 requests. Now with the same resources, it's catering 3,500 requests. If
Sure.
you have such quantifiable numbers to conclude your examples, um, doing that would be a great, because like Meta do have that impact driven culture.
Okay.
That's the one thing. And in terms of system design, if you can think about in terms of data privacy. So, for example, if you are being asked to design a Twitter kind of a thing, right?
Mhm.
Asking questions like whether do we need data localization, the data needs to be in the same region where the user resides. Is there any requirement against policies against data retention? Do we have to make sure that data gets deleted after a certain amount of time? Asking these questions
Right.
will also make you more aligned towards what Meta really values. So yeah,
Okay.
these are the small tips I usually try to give the candidates who yeah, applying for Meta. They will allow us to do that. So
While I have you here, are there any other system design tips that you can give me off the top of your head?
yeah, so one is this that do talk about data privacy and
Hmm.
data localization. Then what you can generic like this is very meta specific thing.
Yep.
One another as a interviewer, we do look out for the four different like aspects from a candidate during the interview. One is ability to clarify the question, so it includes functional requirement, non-functional requirement, effort like a resource estimation in terms of QPS or memory requirement in terms of how much storage would be required, those kind of things. That is one part of evaluation, like how well you can scope out the problem. Second part of evaluation is whether candidate can at least come up with a working solution. Whether it's not about like scaling it up, whether at least he can think about something which will work for a given problem. So that is a second evaluation. Third is like scaling up for the meta kind of scale traffic. So basically, how well your solution can scale up. The fourth is technical communication. So how easily you can articulate your ideas, or how easily I can communicate with you if I have any follow-up questions or those things.
Sure.
So these are the four areas which like usually interviewers evaluate candidate on. I usually recommend to follow this framework, like first thing functional requirements, second non-functional aspects of the system design, writing it down. Third is
Hmm.
estimation. Then like these three things takes care of your first evaluation point, scoping out the problem.
Yep.
Then I usually recommend to write down API specs. Like what are the APIs you think about functionalities that needs to be there, and what is the request response for that. And once you have API design, I recommend to come up with like very high level context zero diagram about with very high level components. Like these two parts, API design and high level design, takes care of the second aspect of evaluation, which is like coming up with a working solution, right? And
Yep.
once you have that working solution, I usually recommend people to write down key aspects, key problems which they can think about. Let's say, for example, if I'm asking you to build a Uber, right? Once you
Hmm.
have working system, like high level design, you can think about like key problems which you can solve about. Like one of those things could be pricing, how you decide the pricing of your cab ride, how your driver allocation algorithm, or it could be like about it could be about like whether do you want to prioritize customers or those things. So you can come up with like very high level problems, like different kind of problems which you can try to solve, and then go back to the interviewer and ask like, what do you think? What kind of what area you want me to go deeper into?
Okay.
And yeah, and that's where from where you try to get a points for your third evaluation point, which is like scaling up the system. We'll talk about scales and everything. So
Okay.
yeah,
Cool. That makes sense. Thank you.
cool. Do you have any other questions?
I don't think so at this point.
Sure. Cool.
I
I
do
think
have
like you.
a
Mhm.
I do have a Facebook interview phone screening coming up, so I'm just preparing from
Okay.
a technical standpoint
Oh,
initially. And then if
oh,
I
if
do get
you
to the
have phone screen,
on-site,
Mhm.
sorry, go ahead.
Yeah, yeah, please go ahead. Yeah.
Yeah, I was just going to say that if I do get to the on-site interview, then
hmm
I'll need to focus on system design. But right now I'm focused primarily on just getting through the phone screening.
Cool, awesome. And yeah, for phone screening, I think coding is good enough. So, and that's the right strategy to do. Yeah.
Cool.
Cool, awesome. All the best for your phone screen. Yeah.
Thank you. Yeah, I very much
Thank you.
appreciate it.
Bye-bye.
And yeah, have a good day. Thanks.
Yeah, thank you. You too. Bye bye.